I built a bunch of SQL query executors for an open source relational database management system called BusTub. Check out my previous video if you don't know what BusTub is, but it's basically an educational database management system built by the database group at Carnegie Mellon University. It comes with an interactive shell, just like any other DBMS shell, but it isn't fully functional yet, and the idea is that students build out the critical components of the system to get it up and running. The assignments in the graduate level course CMU 15445 challenge students to implement the system in stages, and in this video I'll go over how I completed the third assignment, where I implemented a whole array of SQL query executors as part of the query execution layer in BusTub. I also implemented some optimization rules as part of the optimizer component. These query executors make use of the extendable hash table from assignment 2, which I've already implemented, so if you haven't seen that video, the one that's on the screen right now, go check that out. I haven't finished all of the executors yet, just because there's so many to get through, but I have implemented the most important ones, and at this point I consider my BusTub implementation to be in a mostly working state. I can now use most of the basic SQL queries in the system and get good results. Obviously there's still lots to do in terms of optimizations and concurrency control, but the BusTub shell is now in a mostly working state. This assignment was definitely easier than the first two assignments in terms of the C++ knowledge that you'll need to learn. In fact, I didn't really learn anything new on that front. This assignment, it's way more tedious than the last ones just because there's so many tasks to complete. The real challenge in this assignment is figuring out the interfaces that are used within the codebase. You have to get really familiar with all of the different classes and their methods, and there's quite a few to go through here. I definitely didn't gain as much C++ knowledge from this assignment as I did from the last two assignments, but I don't blame the Carnegie Mellon database group for that because their main goal is obviously to teach database engineering, not to teach C++ development. The assignment is still world class in terms of teaching people how SQL queries are executed under the hood in a DBMS. So from this diagram we can see how assignment 3 fits in with the overall BusTub implementation. So when a SQL query comes in to the shell, it hits the query processing layer. It gets parsed, then sent to the binder. The binder is an intermediate step that prepares the parsed input to be turned into a plan tree. The planner comes up with a SQL query plan, and it's sent to the optimizer to obviously optimize it and figure out the best way to execute the SQL query. It's here where we implement some of the optimizations that are done in the optimizer. And then once the query plan is finalized, it's sent off to the query execution layer. And this is where the bulk of this assignment is spent building out these different executors. And the idea is that in every SQL statement, each operator is implemented with a query executor. So here we have select and order by. Select will be handled by a scan, and order by will be handled by a sort executor. And we can see that the query execution layer takes advantage of the storage layer, which we've already implemented, the buffer pool manager, and the extendable hash table. Specifically, the extendable hash table is used for storing table indexes, and the buffer pool manager is used in the extendable hash table. A query plan is a step-by-step set of instructions for how a DBMS will actually execute a specific SQL query. It consists of a tree of query executor nodes. Each node represents a single executor, and you may recognize some of these as I go through them. In this example, the tuples, or the actual rows from the tables, are scanned by these sequential scan executors and passed upwards through the tree, and our result set is refined more and more as it passes through each executor until we reach the final executor where the final result set is returned. So after some tuples are grabbed from the sequential scan executors, they're passed up to a join executor, which performs a join operation. Then emits the tuples up to this aggregation executor, where aggregation functions are done on them, like count, sum, min, and max. And finally, these values are sent up to the projection, which filters out unwanted values and leaves us with the final expected result set. The direction that data flows within the query plan and the amount of data that's passed between each node is entirely dependent on the query processing model, which lays out rules for this process. The query processing model that we use in BusTub is called the iterator model. In this model, we start at the top node and we call a next function. This calls the child node into action, which may also have a next function, and we keep calling the next function of the child until we reach the leaf nodes. In a leaf node, there are no children, and we instead return tuples to the parent. So in this way, our data flows from the bottom to the top, and for simplicity, we emit one tuple at a time to the parent where it's processed, and then the next function is called again to continue processing tuples until there are no more left. A query plan can be optimized by the optimizer. This is done by physically changing the nodes within the query plan. For example, we may elect to replace our sequential scans with index scans for better performance, provided that there is an appropriate index on the table. Another optimization we can do is remove the projection executor when appropriate. For example, this this SQL statement does not require a projection as it is grabbing all columns. So in this case, we can safely eliminate the projection node. The first executor we implement is the sequential scan executor. This is a special executor because it doesn't have any children. Instead, it interfaces directly with the table itself. The table is stored as a heap consisting of pages from the buffer pool, which contains our actual data. In the sequential scan node, we store an iterator which we use to keep track of where we are in the table as we scan through it. We emit one tuple or row at a time and increment the iterator so that we can get the next tuple whenever the parent calls the next function again. We stop iterating once the iterator reaches the end of the table, where we return false to signal to the parent that we've finished scanning the table. Here's a basic example of a sequential scan when used in a SQL query. Select all from test simple sequential 1, and you can see we've simply iterated through the table and emitted all of the tuples. My implementation can call itself recursively, which simply has the effect of ignoring the current tuple and moving on to the next tuple. There's two reasons why you would want to ignore a tuple. The first reason is if the tuple has been marked as deleted, we obviously don't want it showing up in our final result. The second reason is the sequential scan executor can apply a filter predicate. If the tuple doesn't satisfy the predicate, we don't want to emit it to the rest of the query plan. The filter predicate would correspond with a where clause in a SQL statement, as shown in this example. Later in the assignment, we also implement the insert, update, and delete executors, which you can see here in the output from this test file working as expected. The return values from these operators are a simple tuple describing how many rows have been inserted, updated, or deleted successfully from the table. Another fun executor we implement is the aggregation executor. This allows us to use 4 aggregation functions in our SQL queries: count, min, max, and sum, as seen here. You can see here the results of the test file working as expected. The tuples being emitted show the results of these aggregation functions. Using count on an empty table returns 0 as expected, and using any other aggregation function on an empty table results in a null value as per the assignment spec. I've also implemented the join executor, which uses a naive nested loop join algorithm to actually perform the join. Later, I'll be optimizing the join executor to use a hash join when there's an index available on the table. But here you can see we can now use 2 different join types in our SQL queries: left join and inner join. And you can see here the results from the test showing the join executor working as expected. On the left join operations, you can see if there are no matching tuples in the right side table, then we simply join the left side tuples with null values and we emit that. The most recent 2 executors I've added are the limit executor, which allows us to limit the number of tuples that show up in our final result. As you can see in this query, we're limiting the result set to the first 10 results. And the most recent executor I've added is the sort executor, which lets us use the order by operator. You can see here, we can even order by multiple different columns, one after the other. And we can also choose ascending order or descending order. In terms of optimizations, I've added the index scan optimization rule to the optimizer, which is a component that actually alters the query plan nodes if it detects that an optimization can be made. So here, instead of using an inefficient sequential scan to select tuples from a table, the optimizer detects that there is an existing index on the table which can be used to do efficient lookups. So it literally replaces the sequential scan node with an index scan node. The index scan actually makes use of the extendable hash table I implemented in the previous assignment, which allows us to look up tuples with constant time complexity as opposed to the linear time complexity we would have gotten with the sequential scan. So here you can see the tests are showing that the scan was successfully optimized to use an index scan in the appropriate situation. So yeah, that's it for assignment 3. I've got BustHub running in a pretty good condition at the moment. A little bit more work to go, but I'm really happy with how it is right now. So yeah, thanks for watching, guys. I'll see you in the next video.